Hey everyone, today we're looking at section 5.3 notes. So connecting f prime and f double prime with the original function f. So kind of recap from the last section, we were looking at when an original function is increasing and decreasing and where those extreme values are located by looking at the first derivative. So let's say we had a function like x squared minus 4x plus 3. What we did is we took the derivative, which would be 2x minus 4, and then we found the critical points. Critical points are when derivative equals 0 or undefined. This is never undefined because it's a line, but it is equal to 0 at x equals 2. So then I make my little sign chart. I list out 2 on a number line, and then I dash down, and then the derivative equals 0 at 2. And then I just have to check one point to the left and to the right of that place, because the only place the derivative can change sign from positive to negative or vice versa is if it goes through the x-axis or it's at a vertical asymptote or something. So the only possible place this derivative can change sign is at x equals 2. So I check a number to the left of 2, like 0. I plug 0 into the derivative, and I get negative 4, which is a negative number. If I plug in a number to the right of 2, like 100, I get a positive number. So because the derivative changes sign from negative to positive, this function has a min at x equals 2. Like the function itself would change from decreasing to increasing. And we're going to officially give that a name. What we're going to call that is the first derivative test. So at a critical point, let's call that a specific x value c. If the derivative changes sign from positive to negative at c, then the original function has a local max. Again, this isn't like extreme values, the highest or the lowest, but I will have a local max. And that local may wind up being the overall highest. But so again, if the derivative changes sign from positive to negative at the critical point, then f has a local max. So the derivative could either equal 0, like in this case here, or the derivative could be undefined, like a cusp, like something like this. But in both cases, the derivative is positive and then negative because the original function here is increasing then decreasing, increasing then decreasing. And if the derivative changes sign from negative to positive at the critical point c, then f has a local min at c. So again, here is derivative is negative and then derivative positive, derivative equal to 0 at the specific point, horizontal tangent. So that means the original function was decreasing to increasing, which makes that point a min. And here's like absolute value. The derivative is undefined at corner. So derivative goes from negative to positive, which means original function goes from decreasing to increasing at that specific point. Now we don't have to change sign at a critical point. So again, something like x cubed, if f prime does not, x cubed, the derivative is positive and then stays positive. It goes 0 for 1 point. We'll examine this later. But at this point here, this is neither a min nor a max because it's just always increasing with like kind of a leveling out point. So if f prime does not change sign at the critical point, then there's no local extreme values. And here's a kind of finalizing this idea at the endpoints. So if you're at a left endpoint and the derivative is negative, leaving the left endpoint, that means the original function is decreasing, leaving that left endpoint, which means that left endpoint is a local max. If the derivative is positive to the right of the left endpoint, then that means the original function is increasing as it leaves the left endpoint, which means, again, it's a local min. For a right endpoint, if the derivative is negative as you go towards a right endpoint, that means the original function was decreasing as it approaches it, which makes it a local min. If the derivative is positive as you approach that right endpoint, that means the original function is increasing as you approach it, which makes it a local max. So here's like a good 5.3 analysis here. So we start with some function, some cubic, and I want to find min-max points. Okay, so I'm going to take the derivative, 3x squared minus 6x minus 9 plus 0. Again, this is never undefined, so I'm going to set it equal to 0. It's nice that a 3 can factor out of this. So 3 parentheses, x squared minus 2x minus 3 equals 0. And then this factors to x minus 3 times x plus 1. Two numbers that multiply to negative 3 and add to negative 2. So I'm going to list out on a number line those critical points, negative 1 and 3, and then dash, 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 dash. Put a little 0 here and here, because that's where the derivative equals 0. And then let's check to the left and to the right. So now in the factored form, if I put in a number like negative 100, this would be positive because it's just a 3, times a negative would give me that positive. A number between -1 and 3 like 0. If I plug it in, it'd be positive times a negative times a positive, which would give you a negative. And then number to the right of 3 like 100, positive, 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 the result's a positive. So that means the original function was decreasing and then increasing and then decreasing. I just flipped that up. My bad. Sorry, derivative was increasing, then decreasing, and then increasing, which makes -1 a local max and x equals 3 a local min. Okay, so here's some new thing. Now we're going to start looking at concavity. So we've been dealing with first derivative being positive or negative, original function increasing and decreasing. Well, it turns out that actually the second derivative tells me information about the original function as well. And then it tells me actually what the concavity of the original graph is. So here's like the definition right out of the book here. It says a graph, the original graph y is concave up on some interval if the derivative is increasing. What does it mean when the derivative is increasing? If y prime is increasing, that means y double prime is going to be positive. So if y double prime is positive, if the second derivative is positive, the original function will be concave up. And it's the flip of that for concave down. So the original graph is concave down when the derivative is decreasing. Well, if the derivative is decreasing, then its derivative, the second derivative, will be negative. When the second derivative is negative, the original function is concave down. So here's kind of like a little recap on that. When the derivative is increasing, original function is concave up. This means the derivative of the derivative is positive. So let's take a look at that and see what that means. But really what the recap is now we're looking at the positives and negatives of the second derivative. And the positives and negatives of the second derivative are going to determine the concavity of the original function. So let's look at something like x cubed. This is a good one. We'll take a look at. Here's our x cubed again. So the derivative of x cubed is 3x squared. And if you look at this, 3x squared, this is an always positive thing. So the critical points, 3x squared equals 0 at x equals 0. But if you notice, if you plug a number to the left and to the right of 0, it's going to be positive and positive because 3x squared is an always positive thing except for 0 at 0. And what this means is the original graph is always increasing. And that's what I see here. It is always increasing all the way. Except for that one little point where it's kind of like leveling off right here. But now check this out. I take the derivative of 3x squared. I get the second derivative is 6x. So I'm going to put this 6x now also. It's not considered a critical point. Well, I guess it already was. 0 was a critical point. But when second derivative equals 0, it's not called a critical point. That's only when first derivative equals 0 undefined. But it's still a point that I'm going to list now on my number line for candidates for things happening. So I'm going to list out critical points when first derivative equals 0 undefined and second derivative equals 0 undefined. So the second derivative does equal 0 at 0. And then if I check a number to the left, like -1, I get a negative value. If I plug a number to the right of 0, like 1, I get a positive value. So here's what this is saying. What this is saying is that to the left of 0, x cubed is concave down. And that's what I'm saying here. This is a concave down graph. And to the right of 0, the original x cubed graph is concave up because the second derivative is positive. When second derivative is positive, the original function is concave up. So I'm seeing that switch here. I'm seeing second derivative change from negative to positive. So the original function goes from concave down to concave up. It's also interesting that there's two different ways you can write increasing now. So yes, both of these sections are increasing because the derivative is positive. But now I'm going to do increasing concave down. So like, an upward pointing arrow, but bending in the downward direction, and then an upward pointing arrow bending in the upward direction. If you think about the parabola pieces there. So both of these intervals are increasing, but concave down, then concave up, looking at those pieces. So again, here's the recap here. Since f prime is always positive, that means the original function is always increasing. Since the derivative is negative, then the original function is concave down. Since the second derivative is positive, then the original function is concave up. Cool. Okay, so here's two more points on this. So there's our first 2 points. So the first 2 points just talk about, derivative increasing, decreasing. And then the 2 other points is what we were just kind of mentioning there, is that so an original function is concave up on any interval when second derivative is positive, and original function is concave down on any interval when second derivative is negative. And another note, wherever we have this change in concavity, this point where the graph has a change in concavity, and it is a physical point on the graph, we're going to call that point where we change concavity an inflection point. So x equals 0 in this specific case is going to be point of inflection. So an inflection point is where you change concavity. What's interesting is, the calculator can get you x-intercepts, the calculator can get you mins and maxes, but the calculator cannot calculate inflection points. So there would be some more work that had to do that. We'd have to take like the second derivative and find when the second derivative equals 0, solve for those points, or find the mins and maxes of the derivative graph, because the mins and maxes of the derivative graph, the derivative of those places is going to equal 0. So things that, places we can, use our analysis to kind of figure those points out, because the calculator won't give us those points. Okay, so here's another example. So here's a cubic here, x cubed minus 3x squared minus 9x plus 1. So this was the previous one. So it's the same graph as here. So I already filled out x cubed minus 3x squared minus 9x plus 1. I found the derivative was 3x squared minus 6x plus 9, minus 9. And I filled out this first part already on the sign chart. What I'm going to do is I'm going to kind of finish this sign chart here. And now I'm going to take the second derivative of this, which is 6x minus 6. And I'm going to set that equal to 0. And that equals 0 at 1. So I'm going to add this little 0.1 here and do my little dashed line, and then put the second derivative equal to 0 there. Now, if you notice, now I have, instead of 3 sections, now I have 1, 2, 3, 4 sections. But I don't need to change anything here, because the only place that this first derivative change sign was at -1 and 3. So I can just mark each of these buckets here negative. And just like here, for the second derivative, it equals 0 here. So I don't need to check each of these individual 4 buckets. Whatever the sign is in anywhere here, all the buckets are going to be the same. And if the second derivative is positive in any bucket here, everything's going to be the same. Just kind of give you a heads up. It's like, for example, if I do a number to the left of 1 like 0, the second derivative is going to be negative. So I'm going to put little negative tick marks in each of these sections. But I am going to keep the sections separate, because that'll help with my graph analysis. And if I check a number to the right of 1, like 100, this is positive. So each of these buckets is positive. And again, why I do 4 different sections is because this original section is increasing concave down. So increasing concave down. And then it goes decreasing concave down. So negative derivative, negative second derivative, decreasing concave down for original function. So here's that piece. This piece is decreasing concave up. Negative means decreasing for first derivative. Positive for second derivative means concave up. So this is decreasing concave up. And then the last section is a positive, so it's increasing and concave up. First derivative, positive, original function increasing. Second derivative, positive, original function concave up. Cool. So there's my pieces there. There we go. Okay, so a couple more notes here. So here's another interesting thing that's going to lead up to this idea of the second derivative test. If you look at this parabola, if you look, this second derivative, this original function is always concave up on this interval. It's going to be concave up this entire time. This point here, this x value of c, that's going to be our critical point, because the first derivative is going to equal 0. Well, if you notice, if you're concave up at a critical point, that's automatically going to make that critical point a min. I don't need to check to the left and to the right. I can take that physical x value, plug it into the second derivative, determine the sign of the second derivative. So again, when the derivative equals 0 and the graph is concave up, meaning second derivative positive, you're going to have a local min. And then check this point out here. This is still a critical point. the derivative equals 0 at this point c. But if you notice, the second derivative is going to be negative this entire time because the original function is concave down for this entire interval. So at that specific point, the derivative is equal to 0 because it's a critical point, and the graph is all concave down, second derivative negative. So that makes that point a local max. So instead of doing a sign chart and checking to the left and to the right, another way to test for mins and maxes is to do the second derivative test. And what the second derivative test states is, at the critical point, if the first derivative equals 0 and the second derivative is negative, then the original function has a local max at that point. And if the first derivative equals 0, critical point, and the second derivative is positive at that specific point, I plug in that specific x value, let's call it c, into the second derivative, and I get a positive value just at that specific point, then we're going to classify that point as a local min. Okay, so here's a couple final examples here. So I'm going to start out, let's do this one here. So I'm going to start with e to the negative x squared, and I'm going to determine extrema. This is just the plural of extremum, or mins and maxes. Minimum, maximum, minima, maxima, singular versus plural, and inflection points. So if I take the derivative of this function here, the derivative of an exponential function is itself times the derivative of the exponent. So it's going to be e to the negative x squared times negative 2x. And this is never undefined, but it does equal 0 when, let's see, e to the negative x squared, this is an always positive thing, but when x is 0, this entire thing's going to equal 0, because it'd be negative 2 times 0 times 1. So an x value of 0 is going to make the first derivative equal to 0. So that's my critical point. Now let's take the second derivative. So now I have to do a product rule because it's two things multiplied together now. So I do the derivative of negative 2x, that's negative 2 times the second function, plus the first function, negative 2x, times the derivative of this function. So the derivative of this would be, again, itself times negative 2x. So that negative 2x times this negative 2x would give me a positive 4x squared times that original function. So again, that second part would be this thing times the derivative of that, and the derivative of that would be negative 2x times e to the negative x squared. So then that'd be times that negative 2x. Okay, so again, this thing is never undefined. It does equal 0. It's kind of tough to tell, but what I can do is I can factor out a negative 2e to negative x squared. And when I do that, I get 1 minus 2x squared. So check this out. This, again, is an always negative thing. Negative 2 times e negative x squared, that's an always negative thing times this. So I'm going to take this specifically and set it equal to 0, and I would get, if I solve for that, so if I set this piece equal to 0, 1 minus 2x squared equals 0, I get, 1 equals 2x squared divided by 2, 1/2 equals x squared, square root both sides, I get plus or minus 1 over square root of 2. So these are two places where the second derivative equals 0, so those are going to be my inflection points. Now what I also want to do is, I want to take this critical point, the point that made the first derivative equal to 0, and I'm going to put that into the second derivative. And if I do that, I'm going to get negative 2 times e to the 0 is 1, so negative 2 times 1, plus 4 times 0 times 1, so that's all 0. So I get negative 2 plus 0 is negative 2. And here's what that means. By the second derivative test, at the critical point, the original function is concave down at the critical point because the second derivative is negative. So since the original function is concave down at the critical point by the second derivative test, x equals 0 is a local max. So I didn't have to do a sign chart and work my way left and right. Check, so, if the original function is increasing, decreasing, and vice versa. What I can do is take the physical critical point, plug it into second derivative, and just check the sign of the second derivative. If the second derivative is positive, that means the original function is concave up and it's a min. But in this case, the second derivative was negative, which means the original function is concave down at the critical point, so it's a max. And then for this last example here, It's just like, what do I know looking at a derivative graph about the original function? Well, check this out. If this is a derivative graph, what I know about f then is, since the derivative is positive from 0 to 4, the original function has to be increasing this entire time. And then from 4 to 8, if you notice, the derivative is negative. Or what do I know when the derivative is negative? When the derivative is negative, the original function is decreasing. And then at 4, the derivative changes from positive to negative at the critical point. I know 4 is a critical point because it makes the derivative equal to 0. So since the derivative changes sign from positive to negative at the critical point, it makes x equals 4 a local max for the original function. Now these 2 points also make the derivative equal to 0, but they're also endpoints. So let's do that. So at this point here, at the left endpoint, the derivative is positive, which means that the original function is increasing away from that left endpoint. Since I'm increasing away from a left endpoint, it makes that left endpoint a local min. And then at 8, if you check this out, the derivative is negative. What that means is the original function is decreasing as you approach that right endpoint of 8. If the original function is decreasing as I approach a right endpoint of 8, it makes 8 a local min. And then if you notice, the derivative is increasing here. So the derivative of this graph will be positive. Well, the derivative of the derivative is the second derivative. So the second derivative is going to be positive from 0 to 2, which means the original function is concave up. And you can say the same thing from 6 to 8. This graph, the derivative graph, is increasing from 6 to 8, which means its derivative would be positive. Its derivative is the second derivative. So since the second derivative is positive, the original function will be concave up. And then from 2 to 6, this graph is decreasing. Since this graph is decreasing, its derivative will be negative. Well, the derivative of this graph is the second derivative of the original function. So since the second derivative is negative, the original function has to be concave down. And I will have points of inflections at 2 and 6. And I know that because this graph goes from increasing to decreasing, which means its derivative will go from positive to negative. Again, its derivative is the second derivative. So since the second derivative changes from positive to negative at this point, then the original function will have an inflection point, and vice versa at 6. So this graph changes from decreasing to increasing, so its derivative will change from negative to positive. Its derivative is the second derivative. So since the second derivative changes from negative to positive, the original graph will have an inflection point at that point. So hopefully you had fun with this. It was great working with you again. I will see you next time. Take care, everybody.